Okay, in this video, we will run the ARIMA model. So I have some code here. The first thing we need to do is pip install pmd ARIMA. So we need to do this in the command prompts. All I know this for certain is that are the instructions saved here. So we go back to Anaconda. We have Anaconda here, and we need to open up the command prompt interface. This is the command prompt interface. You type in pip install pmd ARIMA, press enter. And this is one of the issues with Python, right? Sometimes you want to run a model, but before you run the model, you need to pip install a package first. And then after you pip install the package, then you can install the library, and then you can run the model. And this is one of the reasons why I don't like Python, because sometimes I want to run a model and I don't realize that the reason why the model not running is because I don't have this package installed. Now we can see from this example here, it's relatively easy to pip install a package. Well, it's supposed to be, sometimes give trouble. But I mean, this does take time, because sometimes it takes a lot of time just trying to figure out what's the problem and how to solve the problem then. Usually the fixes would be a very simple fix, but let's take some time. I was with a lot of time trying to figure out these things now. So anyhow, we have pmd ARIMA installed. Now the next thing we have to do is import pdm ARIMA. So I'll copy this code. To get this notebook here, click paste. So we see we didn't get any errors, and the reason why we didn't get any errors is because we previously just pip install pmd ARIMA. Now we can import it. Now we can see in previous code we will import pmd ARIMA or import the library as something, but we're not going to type in as and the additional like nickname, because when we want to call pmd ARIMA, we just call pmd ARIMA. We are now going to import other libraries. These are just the comments I'm writing in here. As a general rule, I always put comments when I write my code, and that is because in the future, if I want to run the same code, sometimes I can run into problems. But if I have comments explaining what I'm doing, I can just read comments and say, oh, this is to do that, that is to do that, and so forth. And that is how I retain my proficiency in terms of using these programming languages then. If I don't write these comments, I'll run into problems, because the reality is this is not something you will remember every day. You won't remember import pandas as PD, you won't remember import matplotlib, you won't remember all these things in detail. So what happened is that you'll forget. And when you forget now and you come back some time later, you realize you carry these models. Understand? And this could be a problem. But if you have comments explaining what you're doing, you don't even if you forget, these comments serves as a reminder and helps refresh your mind about how to run the model. So this is a best practice I recommend that everyone should adopt. See the codes working, we have no errors. The next thing to do is import data. Now I know previously the data was here on drive C, but that drive C is now drive F. So I'm switching to drive F and then click run. All right, that's the same WTI returns, the same data file. Same data file was working with before, the previous example. WTI returns. So the next thing we will do is to try to get some basic descriptive statistics. Mean, median, mode, interquartile range. These basic things are descriptive statistics. Insert code here. So the cell count, this is the number of observations, 225. The mean or the average observation is 60. The standard deviation is 16. The minimum value is 3.32. In terms of the lower quartile, middle quartile, which is the median, and then upper quartile, these are the values, respective values here. This is maximum value. So that's basic descriptive statistics. And now to run the test for stationarity. Now in econometrics, we know that sometimes you have a time series and the time series is stick constant over time. Sometimes it's going to increase, it's going to decrease. There's some change in trend then. So if the average value of various statistics, so most likely it's the mean we deal with, mean and variance. If the average value of the mean is going to change over time, then this time series is not stationary. This time series is non-stationary, meaning that it's its moment conditions, first and second moment conditions will change over time. How can we test for this? We can test for this with the ADF test. Well, at least the ADF test is a basic test to test for this. I mean, we know from econometrics, we could run the Phillips-Ferron test, we could run the KPSS test, there's the Perron test to run stationary with structural breaks. There are many stationary tests, but for simplicity for this exercise, just to run this test, ADF test. So note, I just copy the code and I just paste the code here. Code run, I have no problems. Some comments. Okay. Click run. So the test has worked. Before we created the test, now we do in here, we can see here, we apply this test at time series. So we see we apply the test to the time series, WTI. Let's apply the same test to, let's say, returns. See, it's running. So you know the test is working. So the ADF test, this is the test statistics. Test statistics is negative. This is the 1%, 5%, and 10% significant value. So this looks like a left tail test. So we have one furthest to the left. Then we have the 1% furthest to the left. Then you have the 5%. Then you have the 10%. We have the test here, 0.37. You know what? Let me show this with a graph, right? All I could just visually watch this and tell you the answer. I want to show this with a graph. All right, so I want to show the ADF test with a graph. So this is the output here. This is the output here. So you have the ADF values, P values. Now I can just watch the P value here, and I can see that because the P value is 0.9, that means we do not reject the null hypothesis then. But I want to show you the old test statistic approach, the test statistic way. So I'll draw a graph, bell-shaped graph, well, supposed to be relatively. All right. This is 0, 1, 2, 3. All right, this is the first rejection region. This will be minus 2.57. This is the second rejection region, minus 2.87. This is the last rejection region, minus 3.4. All right, so this is the rejection region here. All this reject. So if the test statistics fall anyway in the rejection region, we reject the null hypothesis. This is basic statistics, you know. If you do econ stats, you're supposed to know all of this, but I just doing this because I like to go through these details sometimes. So anyhow, you see the rejection region here. So if the test statistics fall anywhere here, we reject the null hypothesis. The test statistic is minus 0.37. So the test statistic will fall somewhere here. Minus 0.37. So if the test statistic fell here, we would have rejected the null hypothesis. Since the test statistic fell here, that means we do not reject the null hypothesis. And for this test, the null hypothesis is that the series has a unit root. So if we do not reject the null hypothesis, what this means is that the time series is non-stationary. So in other words, this ADF test suggests to me that WTI is non-stationary. I mean, this result is actually plausible because oil prices tend to frequently be non-stationary. So we're just supporting us here with this actual test. So let's go back to the Python. Let's go back to Python. So the ADF test suggests that WTI is non-stationary. Okay, so we have from the code here, we import, so we importing from PMD ARIMA, we're going to import auto ARIMA. So we want to import the ARIMA command. We need to import warnings, and warnings filter ignore. This is to import the ARIMA command. And next, you're going to fit the regression. This is to fit the ARIMA model. All right, so we see here, dependent variable y, number of observations, 225. All right, the coefficient. I don't know what I'm saying. What result is this? This output doesn't know how easy users put the results. Oh, look, we see any results here. This is the seasonal ARIMA results, and this is the basic ARIMA results. The best fit model is an ARIMA 10. Is ARIMA 010. So this is ARIMA, no autoregressive component, one stationary component to make it. So you difference it to become stationary, and then you have no moving average component. This is madness in the sense that basically saying anytime you use non-stationary, and this is the best results. They are on the way, they are making good progress. Speaking of the anti-crime march in Library on Saturday, Minister Brian revealed that he has also requested an in-depth cross-ministry examination of the mass murder incident. And I'm asking the Minister of Social Development, I'm asking the Minister of Community Development, I'm asking the Minister of Youth Development to all come together with me, national security, engage in a case study of what happened in Monaco because it really must have behind it a really big story. Sometimes it's present, sometimes. He says communities and individuals each have a duty to examine how and why crime and criminality is affecting them in the way that it is. Yes, each community should be looking at the question of how crime and criminality is affecting them, to what extent it is homegrown. So I'm going to apply a different code to run an ARIMA model. Let's see how this performs. Okay, this had a problem. Train, the command train is not defined. So let's see if the oh, that's why we didn't training model. So this ARIMA model, this code is run similar to, like, let's see how we run like run network models. The train, all right. This code, just train your ARIMA model first, then we'll run back this. All right. So receive training model first, then we'll rerun this. I wonder if I could remove these rows by. Can I send this up? Yes, I can. So I train this first, then I run the model, And when I run the model, this is the results. So this is the coefficient of the AR1, the MA1, MA2. Are the coefficients significant? Where am I seeing coefficients? This is a Z. I see standard error. Look like I'll have to manually compute the probability for. Looks like I have to manually compute the probabilities or the Z statistics associated with the ARIMA. This is a confidence interval for the Z statistic. Okay. Probability greater than Z. So based on what I've seen here, this suggests that if the lockoff point is 0.1, which is the 10% level of significance, this means we want to do not recheck the coefficient is equal, statistically equal to 0 at the 10% for the AR1, the MA1, and the MA2. At least this is what it's saying. Okay. That's not really good results. It's relatively bad results, but nevertheless, the model is working. Observe that this mark SARIMAX. So this is a seasonal ARIMA max model. So this is not a traditional ARIMA model. This is ARIMA max model. All right.
In response to TV6 News, Commissioner Christopher said policing cannot be static. It requires almost continuous review of plans.
Let's just run this to see if it's working.
Effectiveness and to deliver tactical advantages in treating with a very innovative and proactive.
Okay, so this is WTI.
She says in assessing the available resources.
This is the predictions here. So the model predicted this. It will get one constant value, and this is the actual results. Wow, this model is a terrible model. So we know that the ARIMA model is working, but it's performing poorly. So in other words, we should not use this model to make any inferences. So let's compute the mean squared error. The mean squared error determines the predictive accuracy of the model. So we actually computed here the root mean squared error. The root mean squared error, which is the square root of the mean squared error, is 19.57. I mean, this is kind of bad, kind of big, because oil prices must be anywhere between, well, oil prices right now is almost around $100. But if you're about on average about up to $19 off, so that you can run a forecast and you forecast oil price could be, let's say, $80, when in reality oil price could be $100 or $60. So I mean, if you off by roughly about $19 to $20 off, I mean that is a real, your model not really good. It's not accurate at all. That's performing poorly. That kind of too wide for the error.
And the many agricultural training programs and opportunities available in the country. It's the main focus of the East Agri Expo being held at its Sandhurst campus in collaboration with the Ministry of Youth Development and National Service. It's the fourth time UNIC is hosting a Tech Agri Expo this year in collaboration with the Youth Development Ministry, showcasing the many training and business opportunities available locally.
Recognize that we have an aging farming population, involved in agriculture. What we are trying to do is encourage.
Why do I need to make a prediction? Should I run this code, bud? I must skip this code. I'm gonna run something else.
The expo is open to the entire family, It looks the same though, but aimed primarily at encouraging young people to get involved in agriculture by highlighting the various opportunities available to them. That the ministry's own STEP program open to ages 18 to 35, where participants of the program are exposed to training from University of Trinidad and Tobago FAR campus. In
Okay,
general,
so this specify we wanted an ARIMA like this. So let me specify ARIMA like this. We have two auto regressive components. We have one order of integration, meaning that is non-stationary, and let's give it one moving average. So it's an ARIMA 211. Let's see how it's going to perform. All right, well, it's working. Well, at least we are certain that the model is working. Performing bad, but it's working. This is going to make some out of sample prediction. All right, so this model makes a 30 out of sample prediction. Let's give it 10. So it looks like 10 here. All right, so we can see here, when we change the out of sample forecast to 10, we would get 10 forecasts. Let's put 5. This is the date, and this is the actual observation. 1, 2, 3, 4, 5, 6. So it should give us 3. So this must be the first observation, and the other 2 is the forecast. Okay. Let's see, 104.02. Okay, so you realize that this is not changing. So I am going through this and I'm showing you how I change the forecast, because a lot of times when you want to run a model, like an ARIMA model, you require to perform a univariate forecast. And you might know, actually, if you're using a program called eViews, eViews could run an ARIMA model, but eViews can't make an out of sample forecast. This is showing you here how to make the out of sample forecast. Simply running back the same code. All we changing here is this number 30 to whatever number we want. So if you want 30 of sample forecast, you write 30. If you want 1, you write 1. If you want 2, you write 2. If you want 5, you write 5, and so on. This is how to run an ARIMA model and generate a forecast with ARIMA modeling. So this was relatively a short tutorial. We ran the ARIMA model. The model performed poorly, but it worked. We are sure that it's working. And we are able to generate a forecast, and we are able to run the stationarity tests with the ARIMA model. So this is the code to run the ARIMA model in Python. So I'm going to end this video here.